So I am Colin White. I'm a research scientist at RealityEngines.AI. And today we have a lot of exciting talks and demos for the next 2 hours. So I'll give a talk on deep recommender systems, and then I'll hand it off to my colleague Siddhartha, who will show you how to build your own deep recommender system in a Colab notebook using our service, and then how to integrate it into real applications. Okay, so I'll start out with a quick overview of Reality Engines. So Reality Engines is a cloud AI service where you can go onto the website, which is RealityEngines.AI, and then we have several use cases, including personalized recommendations, real-time forecasting, and fraud detection. So it's really easy to click around. You just click your use case, then there'll be a page to upload your own data set, and then you can it's easy to click the specifics of your model and then just start training the model right away, and then you can deploy your model. So if you stick around for later in the talk, you'll be able to get access to to train and deploy your own models. Okay, so now I'll talk about deep recommender systems. Oh, and the other thing about Reality Engines is that we're doing a lot of really cutting edge research in deep learning. So we have a lot of cool research on neural architecture search, debiasing machine learning algorithms, and incorporating logic rules into deep learning. That's all on our website too. Okay, so now I'll talk about recommender systems. Okay, so many of us interact with recommender systems many times a day. Every time you log on to Amazon or Netflix or YouTube, all the suggestions for videos or products are typically powered with recommender systems. In fact, Netflix says that about 80% of all the content watched by its users comes from personalized recommendations. So this means that if they make a 1 or 2% improvement to their algorithm, their profits will increase by a lot. So recommender systems are a very important area of study for many people. Okay, so now I'll just go over some quick definitions of recommender systems, and then I'll talk about some baseline algorithms, and then I'll get into the deep learning techniques. So if you've seen other machine learning problems like classification, there's typically one data set, whereas recommender systems typically has 3 data sets. So let's go with this example of Netflix. So first we have the user attributes. So that'll be like the age of the user, the city they're living in, and so on. And then the next data set is the item attributes. And this will be like the average rating that everyone's given that movie, and maybe the genre of the movie, and so on. And then the final data set is the most important one, and this is the interaction data. So this is like a matrix where on the rows are users, the columns are movies, and then every entry in the matrix is the rating that user is given that movie. And so this is typically very sparse because most users have not seen that many movies, and most movies have not been watched by that many users. And then the goal of recommender systems is to so there are 2 typical goals. One goal is that we can take in any query of a user and a movie and output what we think the user would rate that movie. And another goal is to just query one user and output a ranking of all the movies. So output what we think would be their favorite movie, their second favorite, and so on. And another thing to note is that I said that every cell is a rating, but this can also contain a lot more information. For instance, it can contain the timestamp that the user watched that movie along with the rating, or it could even contain like much more complex data. Okay, so another thing to note is that like I alluded to on the previous slide, sometimes there are temporal recommender system problems. For instance, if you think about like a typical session on Amazon, somebody might log on and then search for 5 different coffee makers, some coffee filters, and then look at a few different coffee beans. And then they start to order coffee beans once a month. So this is very temporal data with a lot of temporal patterns. And some other use case like Netflix will still see some temporal patterns, like maybe someone gets more into action movies over time, but it's not quite as pattern as like ordering coffee beans once a month. Okay, so just the thing to note is there are different types of recommender system problems. Next, I'll talk about how to split up the train, validation, and test data. So if you've seen like classification, it's really straightforward. You just randomly split up your data into groups. But remember, the data in recommender systems is like this huge matrix. So for non-temporal data, it's still not too hard. Usually what we do is for every user, we randomly split all the movies they've interacted with into groups of 80%, 10%, 10% for train, validation, test. For temporal data, we need to be a bit more careful because we don't want to have test data leakage. For instance, if there's some very popular item that comes up like in 2020, then if we had randomly if that item randomly got into one user's training set and not the others, then it would kind of be cheating. So typically what we do is select points in time that give an 80-10-10 split for all interactions that have occurred. Okay, and then every data point looks like a user and their history, their ordered history, and then if a user has a history of k items, we can actually make k-1 data points where we continue truncating the vector, and then the goal at training time is to predict the next item that the user interacted with. Okay. So next I'll talk about some metrics we can use to evaluate recommender systems. So the two simplest are precision and recall. So if we can imagine the true top-end items that the user likes the most versus the predicted top-end items from our recommender system. So precision is just the percent of the true top-end in the predicted top-end. And recall is like the opposite, the percent of the predicted top-end in the true top-end. Another metric that's very common is NDCG. And this is similar to precision, except we weight the items more highly based on where they appear in the true preference list. For instance, if we get the user's #1 choice right, that's more important than getting their 100th choice right. Okay, so it just takes into account the weight of the items on the ranking list. And then the last metric is coverage. So the idea here is that, say we had a recommender system that just outputted the same 10 popular movies to every single user. Well, that's not very interesting because it's not actually learning the user preferences. And you might say, well, like, what if that is actually the answer? But if that's the answer, that every user likes the same movies, then we don't really need to do a recommender system in the first place. So coverage basically measures the uniqueness of the items over the whole test set. And this is typically a very good measure of how well the recommender system is doing, because it captures how well the recommender system is learning unique preferences among the users. Okay. So now I'll give a quick overview of some baseline techniques. And the first one is what I mentioned on the last slide. We just recommend that the most popular items to every user. And this is usually implemented as like a sanity check for any new recommender system we're building to compare against. The next simple baselines are k-nearest neighbor. So for user k-nearest neighbor, say that Alice likes these 7 movies, and then Bob likes 6 of those 7 movies plus 2 extra movies. So then we recommend those 2 extra movies to Alice. The idea is that similar users probably have similar taste. Similarly, we can run item k-nearest neighbor. And the idea here is that, say Bob really likes this movie, then we look for movies that are very similar to that and recommend those to Bob as well. Okay. The next baseline is matrix factorization. And this was a very prominent technique in the 2000s. If you've heard of the Netflix challenge, this algorithm showed up very prominently in that challenge. And so the idea is that, remember, we have this big sparse matrix of interactions. And basically, we assume that it's low dimensional. And under that assumption, we can decompose this matrix into the product of these two thin matrices, where a matrix, two thin matrices of dimension d. And basically, the intuition is that we're assuming that there's some small number of dimensions that can perfectly reconstruct our matrix. For instance, the user dimensions might be like, are they under 40? Do they like action movies? And so on. We don't actually know what these features are, but we assume that they exist. And once we make this assumption, this whole thing turns into a big optimization problem where we search for the best thin matrices U and V that can reconstruct the original matrix. Okay, so that's just a quick overview of some of the baselines. Now I'll talk about a couple more fine points. So one point is the cold start issue. So say we have like a fully working Netflix recommender system, but then a new user joins Netflix. So then we have no interaction data for this new user. So what do we start to recommend them to get the ball rolling? And similarly, the same thing is true for items. Maybe a new movie was just released, so it's added to Netflix, but nobody's watched it yet. So how do we start to recommend this? And typically, in order to handle this problem, we need completely separate algorithms that highly depend on the user attributes and the item attributes. And then another fine point is that AutoML can be very beneficial for recommender systems. For instance, if we think of some other machine learning problem like object detection, the problems tend to be like very similar in the like high level structure, but recommender systems are typically two different applications, can be extremely different from one another. For instance, the matrix might be very sparse versus less sparse, or it might be dominated by user interaction data or item interaction data, or everybody might have highly personalized history versus more popular history. And so there are these many high level attributes that really make the problems different from one another. And that's why AutoML can really help if you have some algorithm that can automatically find the best architecture for your model or the best hyperparameters. You can see a lot of improvement there. Okay, so now I'm going to talk about some deep learning techniques. The first algorithm I'll talk about is neural collaborative filtering. And if you imagine the matrix factorization algorithm from a couple slides ago, we can just take that product between the two thin matrices and replace it with a neural network. Okay, so if you look at this picture on the right, so we have as input a pair of a user and an item, and then we just take their raw features and put them through a neural network. And then the neural network outputs some score, which is the rating that it thinks that the user
I think the speaker somehow got disconnected. He's rejoined right now.
Yeah, I'm still connected. You can hear me? Okay, let me just check. I'm just checking with Colin and having him rejoin. Sorry about this, guys. We'll track down what happened in a second. Okay, if Colin doesn't join, perhaps I can pick up his slides. I do have his slides. I just need.
Yes, I see he's joined now.
Okay, there you go.
Hey, Colin, you're back.
Hey, can you hear me?
Yes.
Yeah, sorry about that. I just lost internet.
No problem.
But it looks like
you can
it's
continue.
back now. Okay, yeah, I'll just continue. Hopefully my internet will be good from now on. All right, so I think for me, I was on this slide. Did I cover this slide before my internet went down?
I think you didn't cover the NMF. You finished NCF, I think.
Okay, got it. Yeah, so remember neural collaborative filtering, a neural network approach for matrix factorization. NMF is just a common variant where we ensemble NCF with vanilla matrix factorization. So now actually all the algorithms I've covered up until this point were non-temporal algorithms where they don't take into account the temporal structure of the data. So now I'll talk about some temporal approaches. So typically for temporal data, we use RNNs, and one popular RNN is a gated recurrent unit. And so the idea here is that we learn the temporal structure of the data. For instance, on Amazon, if somebody orders coffee once a month, then the GRU will find that in the history and start recommending coffee once a month. So here's how it looks like in the full framework. So we start with the user history on the left, which consists of all of the items they've interacted with, ordered. And then we push this through some embedding layers and then into a GRU, like on
Yeah, seems like we lost him again.
I'm just pulling up his slides on my computer. I can probably pick up and continue the presentation. I just need to get it loaded here. 1 sec. Okay.
hey.
Do you want me to?
I think he's back.
Yeah, it looks like.
I guess probably you can try maybe just turn off your video. I'm not sure if it's going to help because of bandwidth or something else problems. Maybe you can just turn off the video.
Yeah, it looks like my whole internet is going down, but maybe I can try one more time, and then if I
if not, Colin, I can maybe take the rest of your slides. So.
Okay. Yeah. So how about I try one more time? If I lose internet again, maybe you can just take over.
Yeah, I'll take over.
Okay. Hopefully it'll be fine this time. All right. So. Okay. So I was talking about this temporal temporal model for deep learning. Actually, where did I go out this time? Or I can just explain this. So we start with the user history on the left, which is ordered, and then we feed that through some embedding layers. Then we feed it through a GRU, which will learn the temporal patterns in the data. Then we feed this through some fully connected layers, and then it outputs a bunch of predictions for all of the items that the user has not interacted with. Then we compare this to the next item that the user actually interacted with and take the cross entropy loss. Okay, so another common approach is to replace the GRU with a attention model. And the idea here is that we actually saw, if you're familiar with like NLP literature, everyone used to use RNNs for NLP, but then they found out that actually attention works better. So the same is true for recommender systems. So we can just replace the GRU with an attention layer. And the idea here is that the attention layer will learn the important items from the user history that'll be beneficial in making recommendations. For instance, if a user has watched a couple of very popular movies on Netflix, and then they've also watched a couple really niche movies, these niche movies will be more important in determining the next movies that the user watched. Okay, and this attention model will also be helpful when there's a lot more enriched data in our problem. For instance, if we imagine like an Airbnb recommender system, the user attributes might include past reviews the user's given, and the item attributes might include photos of the Airbnb. So this attention model might match a user's past reviews that mention kitchens to the kitchen photos of the Airbnbs. Okay, so next I'll talk about a few different recommender systems that actually use generative models in deep learning. And first I'll talk about variational autoencoders, or VAEs. And this is a very popular generative model. This is a VAE right here on the left. And the idea is that we start with our input vector, and it goes through an encoder, similar to like the embedding layer on the previous slides. And then the output of the encoder is some encoded vector that's lower dimension. We can think of it as like a compression. And then this goes through a decoder that tries to reconstruct the original vector. And so yeah, it's basically like an encoding, trying to compress losslessly. And then for a regular VAE, we would take the reconstruction loss of the original vector with the output vector from the decoder. And the variational part is that people have found that if you add a bit of noise after you encode the vector and then try to decode it with the noise, it trains a much more robust autoencoder. Okay, so we can just fit this VAE right into our framework from the previous slides. So the history all goes through an encoder, and then the encoded vector goes through the rest of the neural network. And same as before, we get the cross entropy loss. But then we also run this vector through the decoder and then compute the reconstruction error. So then the loss will be a combination of the cross entropy and the reconstruction. So this is like a more robust way to encode the user history. Okay, so I'll just quickly mention a couple more promising approaches that use GANs, or generative adversarial networks. So in the first work, this team was studying a fashion problem that had image data as input, like on the left here. So a user has some, maybe they've bought some of these shirts or shoes, and then they want to build a recommender system that recommends new things for the user to buy. And typically with image data in recommender problems, we have a standalone object detection architecture like a CNN that encodes the image into features, which are then put into the recommender system. But in this work, they showed that if we simultaneously learn the CNN and the recommender system, the CNN will be more fashion aware and get better predictions. And then they also found that they can use a GAN for the object detector, and then the recommender system will have this really cool new feature where it can actually predict new items that were not in the set of items. So it's like so it's predicting brand new products that don't exist. So if everything to the left of this dotted line are images that the recommender system invented on its own. So this is like a really cool future application of recommender systems where they can actually recommend products that don't exist yet, but might be very popular based on all of the user history. Okay, and then one other new interesting approach is this team that was studying reinforcement learning based approaches for recommender systems, which I was not able to talk about in this talk, but this is like a really promising approach for recommender systems that kind of learns the trends of users better. The only downside is that this typically requires like a ton of data because every user has an environment and actions they can take. And so in this work, they trained a GAN to mimic user behavior to train their model much better. Okay, so these are two like really interesting, promising future work which use GANs. Okay, so that's all I have to talk about today. And so now maybe I can look to see if there are any questions first, and after that I'll pass it on to Siddhartha. So there's one question I see: how does mimicking behavior of user align with understanding what to recommend? So basically, yeah, I wasn't able to talk about this approach too much. I can actually post like a paper in the chat later, but the idea is that there just isn't enough data to train the recommender system to recommend new items, and so they trained again to mimic the behavior, and that just allows more training data so they can better understand what to recommend in the future. Maybe I can look at some of these other questions. Okay, so one, where to start, content or collaborative? Content approaches tend to be a bit simpler to understand, although collaborative approaches tend to be more powerful. So maybe quickly going over content approaches and then trying to dig into collaborative methods. Yeah, so actually I think that these generative, like these approaches using GANs are not quite in the industry. They're more like research papers, but they show a lot of promise, and I can see them being used by industry very soon. For instance, at Reality Engines, we're experimenting with using generative models for all of our deep learning problems. How do we? So I brought up NLP because there's this interesting thing that happened in the field where everyone used RNNs, but then everyone switched to attention models and realized that they worked better. And a similar thing is true for recommender systems. We can use an RNN, but then we can replace that with an attention model, and it'll perform just as well. Yeah, so GANs are very computationally expensive. I think that might be one of the barriers in deploying these types of models in industry. But the field is progressing very quickly with like new types of GANs like WGAN, GP, and things like that. And so I can see very soon that these types of models are feasible for like large scale applications. Okay, I think I answered all the questions that I see. So maybe now I can hand it off to Siddhartha. But you can keep asking me questions in the chat and I'll try to answer all of them. Okay.
Hey, everyone. let me just get my screen shared and then we can start chatting. So I think a couple of people have asked on the Q&A about the hands-on. So I'm just going to, so yes, we definitely would like to kind of get everyone working through actually building a recommendations model and even using it to, integrate predictions into an application. I will sort of, so that we'll work through that in the rest of the sort of the next 90 minutes or so. Let me quickly cover sort of some of the infrastructure and the frameworks needed to use recommendation systems in production problems, and I think that'll be useful to keep in mind as you're working through the hands-on example, because a lot of what you would have to sort of manage manually is going to be handled transparently by the system. So let me share my screen here and get going. Okay, hopefully everyone can see my screen. This is the last slide that Colin was on. This is actually what we're going to try to build by the end of the session, where you get movie recommendations and can interact with it. But what I wanted to, now stepping back and talking a little bit about like the overall process of incorporating recommendations into a product or application. There's sort of a series of steps it takes to get it into a working production application. And even before you get to building a model, you have to start with making sure you're collecting the right data from your application that can be used to train the model. You have to collect it at scale. Some of these models are very data hungry and require collecting a fairly substantial amount of data before you can train something meaningful. Depending on your approach, deep learning requires more or less sort of like requires less feature engineering. Classical methods often require more careful feature engineering. Either way, there's some degree of like normalizing data in a manner that the model can train on, consume, and operate on. You build a model, you have to set up infrastructure to serve the model, very often recommendations. And today we're going to focus on some of these real-time recommendation use cases. And in real-time use cases, there are considerations of latency and scale and making this prediction available in time to impact the user's action. And finally, when you have this all done, you can run it in your application and have personalized recommendations. One of the key things is in these real-time applications, there's the pipeline that builds the data warehouse that's used for training, but that has to be reconciled with a real-time pipeline that is feeding the model for prediction. So even ignoring the problem of like online retraining or continuously retraining the model, you need to be able to get the latest user history to the model for like fresh predictions. And this starts out simply. I mean, it might, when you do this as a prototype, this might seem quite straightforward. And over time, the complexity in this part of the system grows a lot. There's the problem of keeping featureization during training and prediction time in sync, merging the older user history with the real-time user history so that the model has access to the full user history, but also recent user history. If there's featureization, there's often a need to cache features or pre-compute them, and making that available as code changes, as versions change, and so on, becomes challenging. Finally, within the context of online retraining and so on, these models have to be monitored. You have to make sure you're not pushing a bad model, and all of this leads to there are a lot of promising techniques, but very often the more advanced techniques can end up blocked behind just the infrastructure to run this. A good example, as like Colin was talking about, was in reinforcement learning, where not only do you need the real-time access to the user's actions, you need to track the outcome of particular predictions so that you can feed that back to the model and it can update its reward state and so on, to allow the policy to apply in reinforcement learning, right? So you're not just looking at recent user actions, you're also looking at recent user actions joined to the predictions that drove those user actions. All that to say that, there are a couple of common problems that show up here. You know, collect data in a data warehouse, but that data that you use to train the model turns out to not quite be what's available at prediction time, and having to you know, rebuild the model in a manner using features only available at prediction time is a common pitfall that people get into. So there's been a lot of tooling that's come out to support this, and these are very capable tools and frameworks and so on, and you know, putting them together helps build such systems, but it's a fair bit of work because there's a lot of assembly to get all of this working as expected. So for today's workshop, I want to concentrate on this problem of building a real-time recommendation system where the user's history is being fed back into the prediction system as the user interacts with the system and the model. And so, you know, let's get started. So I have the link presented. I'm going to paste it in the chat also, just so that everyone has access to it. Let me pull this up, and I'll switch my screen to that. So when you click on that link, bit.ly/re_streaming, you should be taken to Google Colab workbook that has the setup for today's workshop that we'll be working through. Hopefully, all of you who want to try that are able to open that and get to that workbook. Let me know if there are any problems here, because I want to make sure that everyone who wants to access it is able to access it before I move on. Okay. Hopefully, oh yeah, so I see Colin answered the question. Yeah, so we'll just okay. So if assuming everyone has the notebook open, I'll get started. So as Colin mentioned, Reality Engines is an application that allows you to build deep learning models in the cloud across a couple of different number of different use cases, and the one we'll focus on for today is the recommendations use case. So the first thing we'll do is in this workbook, which is hosted in Google's Colab, which is a tool that Google has made available for the community to be able to like try and share try code and share scripts and so on in the cloud. We'll be able to use it to run the various Python examples and so on to interact with the Reality Engines service. On the workbook, there's a link. The first link is a sign up link for creating a Reality Engines account. And I'll walk through that first so that everyone here can sign up for a Reality Engines account. The system is currently in beta, but everyone, when you sign up through the given link, will allow you to get a free account for trying out the service. So if you click this link, you will be taken to a page which allows you to like get access. Let me just copy this link because it has the token. Okay, so you can sign up with your Google account, or you can sign up with your email address. I'll sign up with an email address because I already have an account under my Google account. Once you so pick a username, and that's not what I want to do. All right, so when you sign up, it'll ask for an organization name, and you can pick any name you want. I'll just call it Streaming Workshop and get started. It'll ask you to verify your email. You can do that from if you have easy access to your email account. Otherwise, you can just get started. So if some of you have a key from the last workshop, you can certainly use that. It'll work with that account that you had before, and it'll create a separate project. So there's no problem using a key from the previous workshop. For those of you who are trying this for the first time, do let us know if you have any issues with the sign up process or getting started with an account on Reality Engines. So let me go back to the screen before I go to the next step. Before I go to the next step, and make sure that we can start working through this workbook. So the workbook itself, each of you will have your own copy. You want to set it up and connect. So I'm going to have it connect to a machine. And so now I have my workbook running, and the first thing I'll do is set up our client, set up the clients for accessing Reality Engines. So the way the workbook works is each of these code cells can be run, and you just click the play button to run them. And if they run successfully, it will print out the output of what it done, show you some information on what happened, and you can go on to the next cell. So this first command just gets the Reality Engine client installed on the host so that we can call the service. I'm going to import a couple of libraries that I use later on in the notebook. These are just to support displaying some of the information in the notebook and accessing the time and so on. So I'll run that too. And the next step is important because we're going to connect this workbook to the account that you created on Reality Engines. So let's go back over to the Reality Engines website, and the first thing we need to do is create an API key so that we can authenticate into this account from that workbook. So I'll click on create an API key here at the bottom. You can also get to it from admin, but let me just keep it simple. So we can create an API key from here, pick a name, doesn't matter too much what you call it. It will generate a new API key for accessing this account and copy the API key. You can either just select the text and copy it, or just click the copy button next to the token. And before you run anything in this notebook, paste the token in where it asks for the API key. This is just Colab's way of letting you enter content into cells, in an easy way rather than editing the code. So once this key is installed or entered into the field, then run the cell. So this makes sure that we have the API key initialized into the workbook. And once we have the API key initialized in the workbook, we can create a client from it. So like I mentioned, this whole notebook is in Python, and for those of you familiar, you probably this will be pretty clear. But what we're doing here is just importing the Reality Engines client library and instantiating a client with the API key that we provided. So this client is now connected to the project that we had created, the account that we had created in this step through the UI. What I'll do through the course of the demo is we'll mostly work on the workbook and use it to do the operations on the project for creating the model and training the model and so on. But I will also show you in the UI what this looks like in the UI, so that you see what is happening, what objects we're creating, and how the model is being managed. So Colin mentioned in his talk that one of the things we have in Reality Engines is a set of use cases that we can the set of use cases that are specific to business cases for which you can build models and train models and so on, right? So in the API, the first thing we'll do is we'll look at the set of use cases that the service provides. So when we run this command, it calls the service and fetches the set of supported use cases that we have defined in the service. Think of these use cases as templates for machine learning. Very often, many machine learning's problems map to different kinds of deep learning models, different kinds of data sets, different kinds of targets, metrics, and so on. And what we've done is define templates that kind of capture the key properties of these problems that are common across different business use cases. So there are problems like user recommendations, which is the one that we're focused on today. But there's forecasting problems, there's fraud and spam detection problems, there's anomaly detection problems, there's problems like predicting whether there's this standard predictive models where we have some inputs and we want to predict a particular target. That's kind of the most general one. So for each of these different problem types, there's a structure for the project that we, that exists, and we will be able to the service will guide us through creating the right objects for that model. For that problem, a model and setting up the problem. So in this case, we're going to work with the recommendations problem. So we'll just set the use case to be recommendations out here. So this is like that API key cell. You just run it to initialize it. And this sets us up to run on the use case. I'll pause here to just make sure that everyone who's trying this is not hitting any issues. Feel free to type or send a question as we're going, because I don't want to get too far ahead of anyone trying it out. Okay. Assuming this is, I've not seen any questions, so I'm assuming this is working for everyone. Let me just check my chat to make sure no one is trying to contact me. Yeah. Okay. So I think it's working for people. Once we have a use case set, we can look at what the requirements for that use case are. So this is quite a bit of information. So I won't try and go through it all at once, but I will briefly describe it. A use case primarily defines a set of data sets that are required for a problem. So, like Colin mentioned, for recommendations, the data sets that we generally deal with are the user and item interactions, the data set that describes what items a user liked or interacted with, a user metadata if it exists, like this is information about the user, and then item metadata if it exists, which is information specific to the item. For a movie, it might be the genre, the year it was published, those kind of things. The user item interaction itself has a couple of columns. It must have a user ID to indicate which user was interacting with the item that they were interacting with, so an item ID, and then a timestamp, which I got a message saying I'm going fast. So let me slow down here and make sure that people are following. I'll also slow down. Maybe that the feedback was I'm talking fast, so I'll talk a little slower. The timestamp column, which indicates when the interaction happened. And for the user recommendation problem that we are dealing with, we assume it's a time-ordered set of interactions. So for this problem type, time is an important dimension. The other optional tables are described here. If there is item metadata provided, it must have an item ID so that we know which item the metadata is associated with. And then if a user metadata is provided, the user ID must be there, so we know which user the data is associated with. Now, one thing to keep in mind is these requirements are a minimal set of requirements. You can always provide more columns or additional attribute columns. That's of course the key point for having these additional tables. But there's no specific requirement on what columns are provided in addition to the ID columns that identify the item. Now that we have an idea of what we are going to be producing and what kind of model we're building. Let's go ahead and create our project. So if you run this next cell, it takes the use case that we defined. So we set the use case above the user recommendations, and it just issues a call to the API saying we want to create a new project, and we get back a message saying that a project has been created with the name movie recommendations, which we supplied, and some metadata about when it was created and an ID for it. We will use this project object that gets returned from the API to make modifications to the project as we go along. So let me reload this page. And you can see that our project has shown up in the UI. I'm going to open this project. We leave it here for now, but this is a good way to see in the UI. The UI is rendering the same information that we saw in the API in a sort of more visual manner. It lists the data sets required. The first one is the key one that's required, which is user item interactions. It has an explanation for what should be in the data set. And if you look at the recommended schema, it'll show you what the data set schema generally looks like to give a sense for what. Okay, I have a so when you go into the Reality Engines page, if you are at the top level, there'll be a link, all projects. And when you click on all projects, there'll be a list of projects. If you run the command in the workbook, then you will find the project movie recommendations. If you've not yet run the command in the workbook, this list will be empty. So make sure that you have been able to run this command successfully in the workbook before looking for your project in the UI. Hopefully that answers the question. All right, so now that we know that we have a set of data sets required, let's start adding data to our project, which we need to do before we try to train a model. The project data sets that we need to add, this is going to be a movies recommendation problem. So we're going to add one data set, which has the movie catalog. This is just the title of the movie and what genres the movie belongs to. There's going to be a users data set, which has metadata about the users that appear in the interactions table. And then finally, the key table, which is the interactions table describing what the users rated for each one. Let's take a quick look at what this data looks like. So we have a concrete idea of what we're building the model on. We're going to, before we upload the data to the service, we're going to first download a copy locally and just inspect what's in these tables. So the first one is the movies data set. We download a copy and run it. So when I run this cell, what it's doing is fetching the data from Amazon S3, loading it up as a pandas data frame. We loaded pandas earlier and just rendering it in the workbook. So you can see that for every movie, we have the movie ID, which we'll use to refer to it in the interactions, and then a title and a genre for the movie. Pretty straightforward. In this data set, we have about 3,800 movies, almost 3,900. The next data set is the users data set. The users data set similarly has a user ID column, which we'll use in the interactions, and has some attributes about the user. The attributes are all, in this case, sort of categorical attributes indicating that, the user's gender, age, and so on. The last and most important data set is the user rating data set. It's a larger data set, so it'll take a little bit longer, but there it's loaded. And it describes quite simply for every row describes one interaction between a specific user, a specific movie, and a rating. For this workshop, we've taken the movies data and limited it to just the 4 and 5 ratings, so sort of only the good ratings. It's possible to include the lower or negative ratings and handle them properly in the recommendations problem, but we won't. We can cover that in Q&A if there's interest in that. And for every interaction, it has a timestamp associated with that interaction. So there are, in this case, there are about 575,000, almost 600,000 rows of data that we think. Okay, people have a different notebook. So let's make sure that you open, let me share the link again to make sure that we're using the same link. Can everyone check that they have opened the workbook using the link that I just pasted in the chat? I'll give everyone a minute just to make sure that they're opened on the right workbook. Okay, great. Looks like maybe some people maybe had a link from a previous workshop or so on, but hopefully everyone can open the link that I just shared. At least some of the people seem to have it. Okay, so let's start uploading this data to the project. I'm going to spend a little bit of time here just so that, because there's a little bit of there are a few options here about how you upload the data, and I want to cover both. And if anyone has questions, do ask, but hopefully this will be clear. So the service can accept data uploaded from a local file to the service, or it can fetch the data directly from the S3 location. There are some restrictions on how we can fetch data from the S3 location. In particular, it has to either be a public bucket so that we know that the data is intended to be accessible to everyone, or it has to be a bucket that has been verified, which is a process that you have to complete through the UI to prove your ownership of the bucket. In this case, we've uploaded the sample data sets to a public bucket, so we'll be able to upload it directly from S3. So what I've done to illustrate both is the movies, the item catalog itself, we'll upload from our local copy into the service. And for the other two data sets, we'll grab them straight out of S3. To do an upload from a local file, we'll take the CSV file that we downloaded from S3 that lives as a pandas data frame in this workbook, save it locally as a CSV file. So I'm just writing it to a CSV file out here, create an upload request using the client, and then complete the upload request, passing it this file object that I open locally and run, right? So that's going to be how the movies data set is uploaded. Uploading from a cloud location like S3 is a little bit easier. You just say create dataset, you give it a name. So in this case, you're going to call the users dataset users, and you tell it where to find the file in S3. And so you give it a regular S3 URI. You tell it which project to load the dataset into, and you tell it for what purpose you're uploading the dataset. So as we have covered before, this problem type supports up to 3 data sets. And so we tell it we're passing it catalog attributes, user attributes, and user item interactions. Let me go ahead and run this cell, and then we can go look at these data sets as they get uploaded in more detail in the service. Okay. So that went pretty quickly. The reason that went so fast is the movies catalog, which I uploaded from my local file, is pretty small. It's only about 5,000 rows, as you saw. So of course that goes pretty quickly. And then since the other two files are coming from S3, the operations are quick because we're just telling the service to go fetch it. And so it'll do all of the fetching in the background and so on, and let us know it's being loaded. So if I go back to my project now in the UI, and I click on the project I was looking at, you'll see that the UI shows us that right now the project is working on inspecting and processing the data sets that I provided via the API. And at this point, it has all of the data sets loaded and ready for use in the project. So before I go through and go back to the workbook, we can quickly look at what it's telling us here. The first step was to set up our data. let's see, someone got a issue with a project ID not being found. Let me, did you want to, for people who have a problem with creating a project, it might help to go back. So let's see, if people are having trouble with creating the project, it might help to go back and rerun this. If you did change notebooks, or you for some reason switched API keys from like a previous API key to a new API key, you might be, your project might be stale. So if you rerun the cell number 9 where you say create project, you should have an updated project and it should have an ID that matches what you're looking for. Yeah, it looks like it could be a mix of old API key and new API key, because if you created the project with a new API key and then went back to the old API key, it might not exist. Well, let me continue, and I think the other people on the chat who can also probably help with help with issues that you're running into. Okay, so the with all the projects uploaded, we can go look at what the API tells us about these projects. And I'll explain the various pieces that's being reported here. So there's a movies data set, and in the movies data set, there are 3 columns: a movie ID, a movie, and a genre. The movie ID is what's used as the item ID out here, so its type is an identifier, and the other 2 items are categorical and categorical list. The service detected that movies looks like a categorical because the data consists of just a text string in each column, and then the genres is a categorical list. It does this by looking for separators like pipes or commas and so on, and sees if they're present in the values. Similarly, it has detected the user ID in the user schema, and then the user movie rating has both the user ID, the movie ID, a rating which is detected as a categorical column, and the timestamp field which it detects as a timestamp column. In this case, because of the data being fairly cleanly organized, the service was able to automatically detect all of the different pieces. But if we can also manually set properties of the various tables. And so, for example, here I can manually specify that the user ID column in the users table should be used as the user ID attribute. So you can manually adjust it. Often the service can figure this out on its own, but if you need to, you can adjust it. And the same thing is visible in the UI. So if I go look at the schema in the UI, let me actually first validate the project. So what we're going to do now is, I'll go back to the UI in a second to go through the data sets, but there's a step in the UI or in the process where we want to confirm that we have all of the different fields and relationships that are necessary to train a model. So in this case, we want to verify that we have interactions with the user ID and item ID. If there's users and items, they're able to join them, join the metadata appropriately, and so on. So this project validation step will check that a project is valid, and if everything is valid, will return true and inform you that there's no errors and the model is ready to train. So if I go back to this page, okay, so I just confirmed the various mappings that were set up via the API and the thing. And if you look at one of these tables, you can see it has information on the file that was uploaded, an estimate of the number of rows, and you can look at the schema that was detected for it. This is the same thing we saw in the API. The UI allows you to explore the same thing. You can also look at some of the data and see that it got ingested correctly, and even look at some basic statistics about the data. This is not the most interesting table, so let me instead look at something like the user movie rating table. So here you can see that we have a little bit more, like, for example, the ratings are distributed between two values, 4 and 5, like we described, with a few more 4s than there are 5s. The timestamp is distributed. We don't really have any statistics to show there. And then the movie ID and user ID, of course, are distributed across a range of values. With all of our data uploaded in the project, we can look at what options we have to train the model. Do a quick time check. Okay, yeah, still good for time. So for training any model, the service handles most of the training options sort of transparently. It's able to infer the right options for the data set and use them to configure the deep learning model, the deep learning training process. Yeah, in most cases, it's probably best to like start with just using what the service has inferred. But for people who are interested, here are some of the kinds of options that are relevant to this problem type. You can control how much data to hold back for testing the final results of the model. You can control some properties of the deep learning system, like the dropout rate, which controls like how well the model handles regularization and generalization. Some features that are more interesting are, controlling whether we want to predict with very short histories, whether there's a maximum history we want to consider. Some of these, again, all of these can be left at their defaults, and the system will do something reasonable for all of them, and we'll use AutoML for cases where some of them can't be determined upfront. It'll experiment with different settings for them and search them as hyperparameters for the training process. So we're just going to leave that alone as is and go ahead and start training a model. So let me go ahead. So when I run this cell, we'll click a model. It'll initiate the training process. It's going to take a while to train. So this doesn't mean that the model is already trained. It just means that the model has started training. If I go back to the UI and refresh it, you'll see the UI has switched to state training. And if you look down, you'll see that we have one model in training that's currently going on. I think someone had a question about streaming. Yeah, so we are going to stream. This is the enable streaming thing, but that doesn't apply till we get to the to a little later in the process. So now that we've got our model running, we can through the API wait for our model to finish training, but we won't you can go ahead and click that cell. If you do click that cell, it's going to sit there and wait for a while, which is going to be about 45 minutes or so. So since we don't want to wait for this model to finish training, we can just stop it, and it'll interrupt it, and we can continue with other things. If we have that running, we won't be able to run anything else in the notebook. So you don't want to leave that running. You can if you tested it, you can just go ahead and stop it and continue. I'm going to skip over the next section. For those of you who are training the model, you can come back here and look at like what you got for your own model and what you what kind of metrics you saw. What I'm going to do is switch over to a model that I trained a little while back, just so that we had something to use and interact with. And you'll be able to use, I'm going to share the keys to that model so that you can check on that. But we'll come back to this later, just so that we can go through the deployment process and so on. But what I've done is I've trained a model previously, and that's what's set up in the notebook here currently. So you can test predictions with that models. But let me first show you what it looks like after the model is completed in that other project. So here's the project I was where I'd started the training before, and in this project, the model it completed training sometime yesterday, and it's ready for both use, and we can go look at its metrics and so on. So when we finished training a model, we go to the metrics. Sorry, there's something I was wondering whether I can show this in a notebook with this key, but for now I'll just show it to you here, and then we can go back to the notebook later. So we can look at the metrics for our training run. As Colin mentioned, common metrics that you look at in recommendations model are NDCG, the mean average precision, which is precision averaged over a couple of positions. So we tend to do this at different points in the list. So mean average precision at 5 is precision considering the first 5 entries in the list, precision considering the first 10 entries in the list. Another interesting metric is mean reciprocal rank. It's like NDCG, a little easier to understand. It basically, if you get a right answer at position I, it adds the score 1 by I to the score. And so if you get it always correct at like position 1, you'll essentially get an average score of 1.0, which is perfect. If you get it somewhere between 1 and 10, you'll get some average number between 1 and 0.1. So what this MRR is saying is that we normally get a movie that the user would watch correct somewhere in the first 5 places or so, somewhere between the first place and the 6th place or so. A key metric that we want to pay attention to is item coverage. So this is important to note that, like, popularity, even though it has an NDCG of 0.2, achieves that by only predicting 1% of the catalog, which in our 3,000 items is about 30 movies, whereas the personalized model gets a higher NDCG, 0.3, but with a coverage of 0.4. So it's predicting almost half of our catalog to users. So there's much more diversity in the set of predictions to achieve the same, achieve better personalization or better precision. So that's our model and the metrics that we have for it. So what we're going to do next is look at how to get predictions from a model. So once your model is ready, you can run through these steps where you enable streaming for your model, and then you can look at what the streaming. We'll go into that. I'll change this to my project so that we can work with the project that I have set up, and then we can go through and see what happens when you turn on these streaming and enable a deployment. Once the deployment is up, you can see it in the UI. We have deployments. Wrong project. So this is the project that's still training. But in this project, we have a deployment that's up and running. And once we have a deployment, we can actually go look at predictions. So it has a sample of the users that were part of the training data set. We can pick a user at random, and we can go see what was in their history and what movies they wanted to watch. So it looks like they like, yeah, it's kind of hard to say what their tastes are in this particular case, but they have a pretty varied taste, and so they get pretty varied recommendations. We can see if there are other users who have more. Yeah, this looks like sort of serious, dramatic type movies, and this looks like what they have on the other side, except for, I guess, American Pie. But yeah, so this allows you to inspect the different recommendations coming for users, so you can get a smell test, understand how the model is working. You can also go look at the predictions in the dashboard and run predictions from the UI. So we can we'll also do this from the workbook, but you can use the UI to test your service. So you can run this request and see the responses that come back. So using the model that I've trained yesterday, so you can go to the prediction step, and you can see here that I've included in the notebook a pointer to the deployment that I set up from the model I trained yesterday, along with this deployment ID. And this is the same thing we ran the UI. We can run it here in our workbook, and we can get our predictions. This will be the same, response that we got from the UI. What we can, it's not a lot of fun to read a bunch of numbers. Each of these numbers corresponds to IDs in the catalog that were provided. But because we have the movies catalog loaded here, we can quickly change that into, maybe I didn't. let me just check. I think. Oh, I ran this twice. You can't run this cell twice because once you run it, it modifies the movie's data. So I can just clear it out, but it's already run. So for the predictions that I loaded, I can use that. Let me just explain what happened there just so that people don't get confused. So the movies data frame that we loaded has the movies item as a column. And this statement here just sets that movie ID as the index for that table so that we can look up the movies by ID. So you have to run this operation once. Once an index is set, you can't set it a second time because the column is no longer available in the data frame. It becomes the index of the data frame. Sorry, that was fast. But if anyone has any questions about that, just type it here and I'll explain that. Once we have our movies table set up to be a lookup table, we can use it to change our return prediction IDs into the actual list of items that were returned out here. So this is the prediction that we got from the service. There are other. Is this the same? Yeah, I think this is just a duplicate or returning 50 users. So I want to just stop here. Just take a minute. If anyone has any questions or things are confusing at this point, this would be a good time to like clarify anything, because next we'll get into the update part where we'll actually start updating user histories against the streaming system so that we can get predictions that change as the user browses the website. Okay. All right. Looks like people are getting their questions answered too. So I'll go ahead and continue. So when we go to a project like this one that we had set up and was training, this one is still training, so it's going to take a while for that to complete. The data that we uploaded was a batch upload of data that is attached to the project. But when we start predicting movies for users, we expect that they will watch some of those movies, like some of those movies, dislike other movies. And we'd like those predictions to be, those events to be incorporated into future predictions for that user, right? Because we've learned something new about the user. And even without retraining the model, we can give the model this new interactions and have it tell us what the user might want to do next, right? So to support that, for the recommendations use case, Reality Engines supports a streaming update to the data sets. Once you have the model trained and before you deploy your service, you can enable streaming, and you can either do it through the UI by clicking on this link, or you can do it through the service. I'm going to go over to the project that I had deployed and show you what it looks like when streaming is deployed to the project. So this project has had streaming updates deployed. And so as part of the item interaction data set, there's a streaming attribute. And if you click the streaming attribute, it shows you how to update the user's information as they interact with your product, with your website, however the user is generating these interactions. There's a Python API, and today we'll also cover accessing this API from JavaScript so that you can build an application with it, a browser-based application with it. We'll first run this from the workbook. So there was a question about the hard-coded IDs in the notebook for get predictions, for get recommendations. The IDs have been hard-coded so that you use the model that I trained yesterday rather than waiting for your model to complete training. So those hard-coded IDs essentially give you access to the model that I have set up in this project that I trained yesterday. So same thing, we're going to do the same thing for streaming because we are all still waiting for our models to finish training and then eventually deploying. For streaming, we're going to use the model that I deployed yesterday. So I have this all set up in this cell out here, And if you say use shared, it's going to use the model that I deployed. If you uncheck this and run this later after you finish your deployment, you can test it against your own model. The other thing that I've done is I've put in a fake user ID just so that we're not all interacting. So if each of you could like put in like either your name or some fake number out here, that way we won't all, clobber our histories. We won't all be writing to the same history. So I just picked, I'm going to pick a random number out here. So I'll just put 1, 3, 2, 4. So I'm going to use that ID. Everyone else can use their own ID. It doesn't really matter if you clobber each other's history. It's just a demo, so that's fine. So that sets up access to our streaming data set and our predictions request. So what we're going to do first is just go ahead and get predictions for this user. Now, when each of you run this, if assuming each of you sort of ran this with a new fake user, essentially what you're getting is the product's cold start recommendation, right? So this was what Colin referred to as the cold start problem, where if you don't know anything about the user and you have no history for the user, what are you going to predict? And in roughly, you predict like what are essentially popular items, right? Like you expect the fallback behavior to be predict items that are popular. And apparently, based on when this data set was trained, the Star Wars is clearly very popular, Forrest Gump was popular, and apparently American Beauty was popular. American Beauty is Oscar winner, so I assume that's a reason why it's popular. But all of us are going to see the same results because essentially, as far as the model is concerned, we're all roughly the same people at this point in time. And then what we're going to do is we're going to submit a set. So someone's asking about, do you break the cell execution? If you are stuck on this cell waiting to train, then yes, just you can cancel execution. Like I can do it again. You can see I'm stuck waiting for it to train. And if I cancel execution, it'll stop. It'll give an error. This error is harmless. The model is still training in the background. This has just stopped the waiting part. And so just go ahead and skip down to the streaming section at the bottom. You can skip over your deployment and so on. You can avoid waiting for that. You can go ahead and we can work through the streaming part. So what I'm going to do now is I'm going to post a set of movie updates to my history so that I can see what will happen to the prediction after the model has access to my latest interactions. So I'm basically synthetically pretending like I watched a bunch of movies or rated a bunch of movies, right? So I'm going to watch, I kind of picked a random list of movies. I think there are a couple of kind of young kid movies out here. So for whatever reason, I end up picking a bunch of them. But this effectively now I've submitted to the system that I've watched these movies as user ID Siddhartha 1, 2, 3, 4, right? And so now I can ask it to repredict my predictions, and you can see that the predictions changed. I've not submitted that much history in this case, only about 10 movies, but I'm already getting Hook and Popeye, which are like kids movies, and my watch was like fairly kids heavy. But I also had Airplane 2 and Gladiator, which are very different kinds of movies from Fantasia and 101 Dalmatians. So the model is predicting a mix. So I still get things like Star Wars, American Beauty, Grease, and so on. So anyway, of course, like we had about 5,000 users and 500,000 interactions. So the average user watches 100 movies or so. So it will take some more history to sort of like converge on a full thing. I can, for example, submit this a second time. And it's like duplicate interactions effectively. And I'll get, you can see it's changing because now I have like even more history still dominated by children's movies. So I'm getting more like Ghostbusters and things like that. There's some horror because of The Night Before Christmas and so on. I think I think Airplane 2 is a horror movie or whatever. But you're seeing the predictions update as the user interacts with the service and sends new predictions to the service. So the service is keeping the latest interactions and merging it with the historical interactions for the user. One of the things that we can do is we can actually if you had used one of the user IDs from here, from the dashboard, you would have actually seen the history show up in the user's history, right? So if I am looking at this user's history, they have history from the training data itself, from what they watched a while back. So this is user ID 987. So if I go and change this user to 987 and I run this cell, so now I'm acting as user 987 as opposed to Siddharth, and I can watch the same, I can watch these movies on behalf of 987. And if I go back to the dashboard, yeah, so these are the movies I just watched. So they've shown up now in the user's history. They've been merged with the user's old history. This is what they watched before. So you can see that they have all the old history in there. And then these are the updated predictions, including the latest history and the old history that was in there. So that gives you, hopefully that helps you understand the flow of mixing like real-time predictions with real-time interactions and getting those predictions evolve in real time. So what I'd like to do now is sort of put all of these together in an application that shows how recommendations and the service could be incorporated into like a working, into a production application or production use case. So if there's people are okay, no questions up to this point, I can go on to the next section, which I'll show how we run this application on a website. So actually, before I go to that, let's make sure everybody has a link. So I'm going to I'll be working with this fiddle, this JS fiddle. Oops, sorry, that's not what I wanted to do. I want to post a link. So you can navigate to that link, and at that link, I've set up a little toy application that everyone can play with, and we can walk through, and it's an easy way to experiment with it. The other thing I want to cover in this application is show you how the recommendations model and the recommendations use case can be used for multiple personalization type requests. So we'll cover both of that there. Can everyone confirm that they can get to the fiddle and are seeing what I'm seeing out here? Okay, cool. So the first thing I'd ask everyone to do, same thing, because we're going to all end up stepping on each other's users and getting different predictions. Maybe copy or give yourself unique user ID in this field. So in the setup, there's a in the JavaScript section of the code, which I'm highlighting here, there's a user ID field. If you can just make that your own user ID before you start interacting with it, that way we'll all keep our interactions separate. So the application consists of 3 parts, 2 of which are really simple and I won't have to spend too much time on. There's a little HTML skeleton into which all of this data will be rendered by JavaScript. You can take a quick look at it, but there's not much there other than these 3 sections for recommendations, related items, and ranking. And this is where I was saying that there are different use cases that we can extract from this one recommendations model or personalization problem. The CSS is just a little bit of styling to get things to look somewhat reasonable, though of course it's quite an ugly UI still. And then the main work which happens in the JavaScript section out here. So let's go into the JavaScript section and understand all the pieces. So the first bit is very much like what we did in the workbook, where we're telling, where we're just setting up the host at which we're going to be making requests, which is the Reality Engines service. There's a deployment ID, which is the deployment ID from which you're going to get the predictions. This is the same as what was in the workbook. There's a deployment token, which is our authentication that allows us to access that deployment token. So all of you are sharing, again, the model that I built, that I set up yesterday for us. There's a little bit of setup in terms of like getting access to the HTML objects, but that's not so important. The next important piece of setup is this REAI tag. We have so the JavaScript API for the service Let me quickly switch over to the UI so I can show you the documentation for this. So when you click on streaming and you look at the JavaScript API, we have a little snippet of code that loads the JavaScript library for like reporting events into the service, and it sets up a function in your in your JavaScript environment that you can call to report interactions. And this is what the setup code looks like. That's what I'm running in that JavaScript code in the fiddle. And this is what an operation to like report a particular interaction looks like. You can either do it on the fly, or you can do it at page load time, all of that. The library is set up to load asynchronously so that it doesn't impact the latency of your page. So out here, I'm just calling the init to pass it the dataset ID. And so this is the dataset ID associated with streaming. These are where the updates will be recorded and shared with the model for predictions. And similarly to predictions, we have a token to authorize streaming. People might be wondering why we have two different tokens. This is because it's not always the case that both of these operations run in the client. Some applications might do the predictions only on the server side. And so if you don't want to expose your prediction token in the client, this way you can keep the token separate. The token for reporting can be shared in the client. Usually writing, because write-only APIs are not that much of a problem. But like the prediction API token can be kept secret on the server side if that's important for your use case. So that's why these tokens are kind of kept independent. The rest of this is just a little, I'm loading the same movie database into the JavaScript just so I can render names instead of IDs. So that's just to keep things pretty. And this code is just to load that and initialize that movie database so that I can render things out here. We don't have to worry too much about get random movies. But now let's talk about the three use cases and what happens, right? So when the page loads, there are three sections. There's a section for recommendations, there's a section for related items, and there's a section for ranking. And these are three different APIs that are made available by the recommendation model that you're in the process of training, or the one I trained yesterday. So we're going to run all three of these use cases. The first use case says, get me recommendations for the user ID that I configured. That's the user ID that you set, and set to your own personal, whatever user ID you wanted to choose. I tell it how many items I want to recommend, and this little bit of code, I'll explain the code down below, says once the results come back, put it in the element with ID hash recommendations. Now, for related items, I pick a random movie from my database. I pick some movie at I've loaded the movie catalog, so I pick one random movie. I set it, and then I say, get me the movies related to that movie for the given user. So this is a personalized related items request. So I'm including both a movie that I want it to be related to and the user for whom I want it personalized. We actually support also related items without a user ID. So, if you had a user, if you didn't know the user but still want to relate items for that, for a given item, you can ask it without the user ID. In this case, I'm passing both. And then the last one is a ranking problem. So I do the same thing. I pick, I guess it's 5 or 6 movies at random from the database that presumably I want ranked. And then I pass those 5 movies in to the API, and I say, get me the personalized ranking. So here, the service will try and rank the list that you've supplied in the order that is most appropriate for that user. So you give it a user ID and a movie ID. All of these are based on the same training idea that you've seen these interactions. You know what like users like. You have a score kind of for each item for that user, and based on that you do that. For related items, there's some additional logic to like decide which items are related independent of like the user involved. So all three of these are run against the service. We can now briefly look like, so this function is a little bit complicated, but most of it is related to JavaScript AJAX. And depending on the AJAX framework you use, it can be more or less simple. The actual API call is quite straightforward. So let me just try and walk through it. And if you have any questions, do type them. Or you set up a request with the token, the deployment token that you supplied, and the deployment ID that you configured. You open a a JSON post request to that endpoint, and you post the content. So the contents, this content is essentially what is being posted to that endpoint. And the endpoint responds with the response that we saw earlier, which is a list of JavaScript movie IDs, right? It's a JSON object containing a list of dictionaries, each of which has a movie ID. So you get that list, and for each entry in the list, you render the movie into these into the page. And so that's how each of these lists are populated. It's the response from the API. You look up the name of the movie in our locally loaded movie database, and they just render the name and the title. If there's a failure, it will report an error. But other than that, that's all that's happening out there. It's just a post of that JSON object and the results rendered into a list. If you finally fire off that request and you wait for it to come back and do this asynchronously. So a lot of this looks a little complicated just because of the asynchronous sort of JSON, JavaScript logic to do this in the browser. And then let's actually, okay, so let's then figure out what happens when I click on one of these things, right? So we're looking at this movie. So when I click on one of these items, it says I'm rating that particular item some number. I click it, it goes and like refetches those and updates it. I don't know. I think. Yeah, okay, there we go. I hadn't refreshed the page after changing my user ID to Siddharth1234, so it was showing me something else. After I clicked it, it just updated. So now it has the user that I'm predicting for out here. So every time I click on this movie, it submits a rating and then does some calculation, gets a new recommendation for it. It gets rated items for a different item. So each time I rate something, all three of these sections update according to whatever I said out there. So let's see what happens when I click on one of these items. So when I click on one of these items, it calls a function to record the rating. And recording a rating simply involves a message using our JavaScript API saying an interaction has occurred on the given movie with this rating and the user. So where is the user getting set? So this is important to note. When I set up the streaming system, with streaming setup, I passed the user ID in the setup saying that all the interactions in this page are going to be related to that user ID. So I configured the streaming library with that user ID as the user ID for all interaction events that are going to come. So when I actually record the event, I just need to pass the movie ID and the rating that occurred, and it'll be attached to the user that the page is currently being rendered for. That's why I needed the reload after the Siddharth1234 stuff happened, so that it had this. So that's how the JavaScript API works with the service to render this like online movie recommendations service. So you can imagine interacting with this and building your product out. I can go ahead and start taking questions on any of that. I'm just going to go back and check if if the model is trained. It's still training. Probably all of us are training at some time, so there's probably going to be a while before those complete. Let me go back here and just walk through these sections because we've not yet finished training. So let me explain these cells. You won't be able to run them right away, but you'll be able to understand what they do. So this statement does the same thing that we could do through the UI, which is enable streaming for a project. It just gives it the project ID and says create a streaming data set at which I can receive the updates. When I list the data sets, the streaming data set will be listed as one of the data set. The user item interaction data set will have information on that. I wonder if I can let me quickly do this. I'll do it on the project that has the train model so that we can actually look at this. I just need this ID. Oops. I'll just copy this project ID out here. Oh, but I'll need to update my API key also. Let me just update my API key too, and then we can do this. I'm just changing this so that we can look at the project that was trained before. Just give me a second to get this. This is the API key that I had for this project. I'll change over to that API key. If I run it, I should get a new client. So now I should be able to connect to this project. Let's just try this, give this a shot now. I don't need to run that again. Oh, but I need to. To say. I actually don't need that. Let me see. Yeah, okay, so it's the first project, so I just need to say movies project is. Should work. Okay, so now this project, you can see that the user interactions dataset has this field called streaming dataset ID, and that's the dataset ID that we've been using for all of the demo and all of that that we've been interacting with. And we can also get the streaming token for that project. This is the streaming token that we were using down below and in the JavaScript page. So basically, we're now attached to this project. We can. I can go ahead and run this. It'll just create a new deployment, which is fine. Oh, maybe not. Oh, I don't have the right model out here. We'll skip that. This model was from the model that was in the previous project. We can actually do this. Actually, it'll get more confusing. I don't want to confuse people with the notebook. Once your model trains, you can run through this. Let me just explain this cell for now, and then we can come back and look at it if you have questions. So this will create the deployment that we saw in the completed project, which will give you the service endpoint. And then from that service endpoint, you can create a deployment token and use those tokens, which is what we set up out here. These are the tokens I'm using out here. So do try to run that once your model finishes training. Let me check. We should be getting close. No, still training. I will let it be for now. Okay, so I think we have about 10 minutes left. So now would be a good time for questions. And if there's parts that I can go back over and help clarify, or if you have any specific details that you want on a step or part of the process. Okay, I don't see any questions coming here, so hopefully I'm not from. All right, let me then just end by saying I hope a number of you got to try and set up your account. That account is free for you to use and try the service. For now, we are making people who are participants in the workshop, give them access to the service to try for free. The deployments in free accounts stay up for 24 hours. Eventually, we have billing and so on if you want to use the service for your production use cases, you can contact us. At the bottom of the UI, let me just quickly show you, there's a schedule free consultation link. So if you want to try, if you want more information or you want to try and work through a particular problem that you have through the service and you want some help with that, do contact us and reach out through this link and set up something to talk with one of us. We'd be very interested to hear about the problems you're working on.
Hi, Siddharth. I see there are 7 questions in the Q&A. Is that already being covered?
Let me check. A couple of them, Austin and so on, have been writing to. So.
Oh, I see. Okay.
Yeah.
The Q&A.
Yeah. So I think Austin and Colin are replying to.
Okay.
I see some open questions. Let me go. Sorry. Well, I'll go ahead. Let me answer some of these. So what is the significance of ranking? And in case we don't have it, can we develop a recommendation system? Okay. So ranking is not something you have to develop separately. It comes out of the recommendation system. When this model like looks at the various interaction histories, it essentially develops a scoring for each user's item. So what we allow you to do is like, if you need to rank a list of items, so let's say your problem is not just give me recommendations, but I have 5 items and I want to know what order to show them, you can call the model with those 5 items and it'll answer with those 5 items reordered according to its notion of like recommendation, personalization. What does it cost to create an endpoint and train and predict on a large scale? This is a, in this particular, for this particular model, we like our service builds on the deployment QPS, like how much QPS you need from the deployment. Do schedule a consultation and we can walk you through details of like billing and so on. It's not well, we don't think it's too expensive, but it's quite reasonable, and the cost of training is quite small for even, you know, a data set with millions of rows. It doesn't cost that much to train a model. Is the recommender system explainable and trackable? I don't quite follow the question about trace back all the interactions to the root state, but what we are developing a framework for explainability where you can understand what features are driving recommendation. So you can basically see like if the user's interaction history had changed in this way, what items in the history are causing particular recommendations to come forward. That is something that we will be making available in a few weeks, not just for recommendations, but for all of the models to be able to explore where those are coming from, like how the model is reasoning. Oh, it looks like someone's training is completed now. So yeah, feel free to click through those cells. Once your training is completed, those cells should start working, and you should be able to follow through the rest of the workbook. If I had to go about the same via command line tool or program, then how we go? Okay, so yes, so everything in the workbook is just regular Python code. So you can take all of those cells in the Python code, paste them into like one Python script, and run them end to end. You wouldn't need to run them through the workbook. They run on any on any machine with the Python library installed. How to start when we don't have data? Okay, that's an excellent question. One of the things that we want to enable, like the reason you can enable streaming before you like even train a model is to support this use case. We have examples of use cases where people don't have data yet, but have a website or a product, and they want to just start streaming data. They want to first stream data, and once they have some data, they want to decide on trying to train a model. And that is something that we will support. You basically collect data for 2 weeks, and then you say train off of the streaming data set. One of the things there is our streaming actually is schemaless, so that you can change what you submit over time, and then only at training time do we sort of try and project out a standard set of features to feed the model. So you can even evolve over time. You can add fields, drop fields, so on, so that it's pretty flexible there. Is there a diagram or slide to show the working model? I'm not like, you can see the model in the UI. You can also interact with the model through the dashboard in the UI. Maybe that is what you're looking for. I'm not sure. I can come back to this question. one of them waiting for the model to be built on, then can we deploy the notebook? This is what's your approach with CLI tools? Yeah, so I think the time for model training exists whether you're training in the notebook or the command line or on a service. Basically, it's a process that takes a little bit of time. But yeah, you could try all of this from the CLI, and other than the sort of unavoidable wait for the model to train, you can test this sort of in a command line interactive loop or whatever tools you want. It's just a Python library, or even like through the REST API, in which case it's just HTTP post requests. Can I explain the metrics reported? Yeah, we have time. Let me actually quickly share my screen again, if that's okay. I think someone was asking about this screen share. Okay, so the metrics for this model, explain the metrics. NDCG. So NDCG basically is like the number of matches you've got divided by a log, like a denominator that grows like the log of the position. So basically, it's a slowly growing function that gives you you get more value for predicting earlier in the list than later in the list. So if you NDCG, roughly, if you predict like exactly like what the user wanted in the order they wanted, you'd get 1.0. Any deviation from that will begin to penalize the model. And so, a model that generates random predictions would be 0. So it's basically a penalty for like how far down the list you're predicting what the user wanted to watch. It's actually quite. It's going to be mean reciprocal rank is like NDCG, but instead of growing like log, it grows by 1 over the reciprocal of the position. So 1 by 1, 1 by 2, 1 by 3, and so on. Yeah, it looks like someone actually replied with all of the metrics that they had. So that looks like they got a reasonable model. I mean, it should be the same thing, it's the same data. So hopefully it's the same thing. There is a documentation, like once your model is trained, like you can click on some of those metrics and get like more links to Wikipedia that explain the metrics in more detail. Traceback, I mean, you have interacted n times. Now you want to see slow motion when the tree graph looks like previous and all the way to the first. In the dashboard, we have some rendering of like the history of like what the users interacted with. Nothing yet quite so sophisticated as interleaving the interactions with the recorded interactions with the predictions, but that's a good feature recommendation. Do you know any source part from well, we make the workbook links. The workbook links will continue to be accessible, so you can look at that. That has links to other information. And I think Colin will also share additional information on papers and so on that you can use to learn more about these recommendation systems. And then also there's a documentation link in the UI at the bottom. You can read a lot more about the service, the API, and how to customize it for your needs. The link is at the bottom of the UI, bottom left corner of the UI. All right, I think I covered all of the open questions. We had a bunch of answered questions from before too. Thanks everyone for attending. It was, I really enjoyed it. Hyperparameter optimization and network architecture search. So hyperparameter optimization is the problem of searching. So one of the problems of deep learning is the models tend to have a lot of knobs, and it's not easy to figure out which knobs to tune. So things like batch size, learning rate, all of these are knobs that control how well the model does. So hyperparameter optimization is a technique used to search the space of like these knobs and find the best knobs for the model that you're trying to build. And network architecture search is hyperparameter optimization at the next level, where you're actually varying the architecture of the network. So now you basically have kind of an unbounded space to search, because you can connect different layers, vary layer sizes, vary layer connectivity and all that. These techniques are for like allowing us to explore the space of parameters and network architectures. The contact details for the free consultation are it's probably if you click on the link on the UI is probably the easiest way to do it. Otherwise, we will share an email address afterwards to reach out. I see someone got an error. So it could, I think